This unit is called Relations and Functions. And so it's the start of the graphing unit. The graphing unit, you're going to want to pick up a ruler and graph paper if you don't already have. You also must have a TI calculator, graphing calculator. Well, you'll need that over the next 3 units. The last 3 units of Math 10C is all to do with graphing. So the first unit is like an intro to graphing. The second unit is studying lines. We're going to learn all about lines and how to write equations of lines. And then the third unit is going to be basically finding the intersection of 2 lines. And how do we do that algebraically? So the next 3 units is all about graphing. So let's talk with today's lesson. We're going to start off with just interpreting and sketching graphs. So it's 5.3. I put that first just because it's a little bit easier than the other lessons. So here's our graph. And it's describing a dog walking. It says describe what the dude is doing during each interval of the graph. Okay, now I'm not asking you to describe what his speed is. I'm just describe what he is doing. Yes, I don't know why I used the word dude. I was trying to be cool, but it's largely in effect, yeah, false, not cool. Let's talk about a couple things first. On a distance time graph, if we have a horizontal line, what does that mean? It's a horizontal line. What? Yeah, Simone? The distance stays the same the whole time. So if your distance is not changing, what does that mean? You are not moving. You are stopped. You are motionless. Okay? Stopped. Yeah. Yeah. Okay, so what if you have a distance time graph? We have 2 different lines. This green line and this blue line. What's the difference between the green and the blue line?
One starts at 0.
Okay, that's one thing. Ben? Who's moving faster?
Green.
The green. So, the steeper the line, the faster you're moving because you're covering more distance in the same amount of time. More distance in the same amount of time. Okay, so here, when it says describe what he's doing during each interval of the graph, how do we figure out what an interval is? A free line, right? And so this interval starts at 0 and ends at about how many minutes? This first line.
12.
About 12, 0 to 12 minutes. Okay? The second interval starts at 12 and goes to about how many minutes? 19 or 18? 18? 19? It doesn't matter. Okay? So we're approximating. The third interval goes from 18 to how many minutes? Here's 20, 24. It's a little less than half. And then the last one's from 24 to about 47 or 48. I'm going to use 48. I like even numbers. Okay. It's about 47 or 48. Doesn't really. Okay, so we're going to describe interval. So we're not looking for actual speed. We're just describing what's happened, and it has to work with our graph. What is he probably doing from 0 to 12 minutes? Walking, the dog. We are walking. And we're walking, and we're walking. And then from 12 to 8 minutes, what is going on? You're stopped. So why might you be stopped for 4 minutes?
The dog is going
to the washroom. Okay, the dog is going to the washroom. Why else might you be stopped for 4 minutes?
Oh, waiting for a crosswalk?
Waiting for a maybe he's talking to somebody. Maybe he's playing fetch. Huh? Playing with a toy? Yeah. Okay. Okay, Kmar. That's not logical. Okay, so maybe the dog's using the washroom, but he's stopped. Okay? Short and sweet. You don't want to write a whole book in these explanations. Short, sweet. Okay, 18 to 24 minutes. Is he moving the same speed or faster? Faster. So maybe he is jogging with the dog. Ooh. Jogging. It's pronounced with a silent J. Okay. So jogging. He's jogging with the dog. And then he decides to, after his 6-minute jog, he returns to walking the dog again. He got tired after 6 minutes. He's a little out of shape. Or the dog got tired. Sometimes the dogs just can't handle it. It's a little dog. All right, so this graph just asks us describe what he's doing. Describe what he's doing. Be very careful that you read the instructions and what they're actually looking for in your description. Example 2. The graph below represents a jogging record. Compare the speed and direction. So now you have to compare speed and direction. What kind of graphs are we dealing with? Sorry, what are our axes? Describe. Distance from home, and time in minutes. Okay, so if our graph is distance and time, how can we use that to get our speed? Because it asks us to describe speed and direction before and after the rest period. What's the formula for speed? Distance divided by, so rate is the same thing as speed. Okay, and your rate that you're moving at is your distance, d over t. So d, which is distance, divided by your time, right? Kilometers per hour is distance over time. So we have two different intervals we have to describe. We have to go before the rest period and after the rest period. So we have 1 and 2. The rest is the horizontal line. So for the first part, it asks us to describe its speed and direction. How would we get the speed then? Distance over time. So what distance did he move? We went from 1 kilometer to 2 kilometers. Is a total distance traveled of 1 kilometer. Over how much time? 20 minutes. That's pretty slow. That's Miss Johnson's speed. Just kidding. Not that slow. No, not that slow. Ryan? Okay, 1 divided by 20. What does that equal? Type that into your calculators. Beep, boop, beep, boop. Yeah, and we get, did you get it? No, what's 1 over 20? No, 1 divided by 0.05 kilometers per minute. Okay, what is his direction? It says describe its speed and direction. So what can we say about his direction? Is it towards home or away from home? Away from home. Home is 0. He's moving from 1 kilometer to 2 kilometers away from home. Okay, now the second part. Let's see if is he going faster or slower? How can you know just by looking at it? Steeper. Steeper. Oh, that's not a straight line. Ryan Wayne, can you pay attention, please? Okay, what distance did he travel now? He went from 2 to 0, which is 2 kilometers, over how much time? 10 minutes. So now he's going pretty fast. It's a good speed. So now his speed is 2 kilometers in 10 minutes. What's 2 divided by 10? What's 2 tenths? 2 tenths. 0.5, that's 5 tenths. 0.2, guys, 2 tenths? Well, sorry. Okay, and what is his direction? Away from home or towards home? Towards home. Headed home. Good. So notice the difference between asking just to describe it versus describing like the speed or the distance or some sort of variable. Okay, turn the page. On the next page are 4 scenarios and 4 graphs. Great quiz question. Match each scenario with its appropriate graph. So we have the 4 scenarios: the height of a bungee jump after a jump, the vertical growth of a tree, the temperature of a cup of hot chocolate as it sits on a table, and Calgary's daily mean temperature. So here's our 4 graphs. Notice what's all similar to them. What's all in common with all 4 graphs? Time. They all have time on the horizontal axis, the x-axis. It's all with respect to time. Okay. Who wants to take a guess at one of them? Scott. Oh, you're gonna write it on the board? Okay. Okay, down. A. Okay, so A, which was what? What was the scenario? Bungee jumper. Why does this make sense? He's bouncing, woo, and then it levels off. Let's finish it off there. Yeah? Graph B is hot cocoa. So what was that above? Option C? Hot chocolate? Why does that make sense? It gets colder. And also it reaches, what should happen actually down here? Plateaus. I like that word. Oops, it goes back up. Right, it plateaus because you're going to reach room temperature. All right, Eric. Okay, on graph C is Calgary's temperature. Now, looking at this time, do you think it's over a short period of time or a long period of time? How long? No. Okay. Most likely, it's a year. Most likely a year. Here's our December, right, to January. Well, actually, it's the other way around. Oopsies. January, December. So most likely it could be a day, and depending on what our scale is, but it also could be a year. We don't know which one. And last but not least, we have A, C, and D covered. That leaves B for growth of a tree. Growth tree. So, yeah, it's growing. It's moving up. It's growing. It's not. Okay. Let's move on. It's the last example we'll do for this lesson. Graphing a situation. Okay, so how do we graph? So there's 3 different graphs we're going to make here. And they're all going to be different. So the first one we're going to do is a speed versus time. Speed versus time. Then we're going to cover a distance from home versus time. And last, we're going to cover a distance versus time. Now, which of these 3 graphs seems like there's the same thing? B and C seem like they're the same thing, but they're not. Distance from home is not the same thing as distance, or you can also call this total distance. Total distance versus time. Okay? Now, the first graph we want to make is speed versus time. So let's look at the situation. Sakura leaves home and travels a steady speed of 100 kilometers per hour for 1 hour. Slows to 80 kilometers per hour for half an hour due to construction, and then continues to for 100 kilometers per hour for another hour. So there's 3 different things here, right? 1, 2, 3. Then what happens? Then she stops for a 2-hour meeting. And then last, what does she do? Returns home at a steady 100 kilometers per hour. What did they not provide us in the last part there? The time for how long. So we're going to have to figure that out. Why do you think it's 2.5 hours? Okay, well, it might be right. It might be right. Basically, what's happening is, how long is the trip taker on the way there? 2.5 hours. There's different speeds though, so that might affect it. So she went at 100 and then 80 and then 110, and that took her 2.5 hours. So we don't know how much, but approximately 2.5 hours to get home. It could be more, it could be less. Speed versus time. So let's graph a speed versus time. So if we estimate, if it took 2.5 hours to get there, 2-hour meeting, and then 2.5 back, how much total time is that? 2.5 there, 2 at the meeting, 2.5 back, 7. So you want to make your axis really long on the horizontal. And what always goes on the bottom on the horizontal axis? Speed or time? Time. So our time in what unit? No, hours. We're going to go up to 7. And it's going to we want to have half ticks because there's times where she only travel at speeds for half an hour. So 1, 2, 3, 4, look, I can count, 5, 6, 7. We're estimating that. What's the fastest speed she gets to? 110. So let's make 11 ticks. Our speed is our vertical axis in kilometers per hour. And we want to go all the way up to 110. So you can go 20, 40, 60, 80, 100, 120. Because we're graphing speed versus time. Now, when it says that she travels 100 kilometers per hour for 1 hour, is our line gonna steadily move up to 1 hour, or is it going to go straight across for 1 hour? We're graphing speed versus time. So at 30 minutes, what's her speed gonna be? Would it still be 100? Yeah, she's moving at a constant rate of 100 for 1 hour. So it is a horizontal line because the whole time she is driving 100 kilometers per hour. It's not distance, it's speed. And she's maintaining a constant rate of 100 for 1 hour. So on a speed time graph, constant uniform motion is actually a horizontal line in a speed time graph. Here's some physics for you. This is what you're going to get in physics 10, science 10 for physics. Okay, so now then what happens? She drives 80 kilometers for how long? Half an hour. So she slowed down, she drops to 80, and then for 30 minutes she drives at 80 kilometers, half an hour. So 1.5. Maybe it's a little much there. And then she increases her speed to what? 110. And how long is she going to, so at 1.5, she increases her speed to 110 and maintains that speed for how long?
An hour.
Till 2.5 here. So I don't know if you need these, right? This was at 1. This was at 1.5. This is at 2.5. Okay, oh, my line looks a little lobby. Don't know, lobby, I just made up that word. Lopsided. Okay, close enough. Okay? Does that make sense there? You don't actually have to do those dotted lines. It's just showing you how it's lining up. So 2.5 hours. I'm going to delete those lines. Now what does she do? She stopped. Her speed drops to 0. So at 2.5, it drops to 0. And then how long is she at 0 for? 2 hours. So at 2.5 to 4.5. So 4.5 hours. Then what happens? She goes up to 100 and just 100, actually, just 100, and she maintains that. Do we know how long? No, till she gets home. Now I'm going to tell you what it is so that you don't have to go back and try it. We're going to figure it out in a little bit, and it's going to be 7 hours exactly. So down to 7, and we're going to calculate that in a moment. Okay, so she is traveling for 2.5 hours, at 100 kilometers per hour. And I'll show you how we're going to calculate that in a second. Okay, so that's a speed time graph. Very different than a distance time graph. Now we have two different graphs we want to make. One is distance from home, and the other is total distance. Okay, now in order to graph distance versus time, what are we going to need? Do we have the speed? Yeah? What don't we have yet to graph distance versus time? Do we have the time? Yeah? The distance. We don't know. Do you know how far she's traveled yet? No. We need to figure that out. Now, there's those three different intervals, those red ones that I boxed up above. So we need to find the distance she traveled. If she travels 100 kilometers per hour for 1 hour, how far did she go? 100 kilometers. So how could you actually get that? Well, remember, distance equals rate times time. How do we get that? Ooh, let's figure out. Remember, rate is distance divided by time. Speed is distance over time. Yes? Remember that? Life is good? If I want to solve for distance and I want to get distance by itself, how do we get rid of time if it's on the bottom? Multiply both sides by t, and the time would cancel out. If we're isolating for distance, this is what you will have to do in physics. So distance is equal to rate times time, right? How fast you're traveling for how long multiplied together will give you your distance. If I'm traveling 200 kilometers per hour for 100 kilometers per hour for 2 hours, how far did I go? If I'm traveling at 100 kilometers per hour for 2 hours, how far did I go? 200 kilometers. We multiply them. Very good. That was a brain teaser there. Good morning. Afternoon, actually. Okay, so we have 3 different intervals. We have to look at those 3 intervals. The first one, how far did we go? How far did we go in that first one when we went 100 kilometers per hour for 1 hour? 100 kilometers. 100 times 1? 100 times 1 gives you 100 kilometers. Okay, in the second interval, we traveled what pace? 80 for half an hour. How many kilometers did you drive? 40, because 80 times 0.5, half an hour is 0.5, is 40 kilometers. Distance is rate times time. The third interval, what speed was she driving at? The third interval above. 110 kilometers for how long? 1 hour, so what's her distance? 110 kilometers. So what's the total distance she traveled then, up till when she got to her meeting? 250. 100 plus 40 plus 110 was 250 kilometers. 250. So on her way home, if she had to remember she was traveling at 100 kilometers per hour constantly? Let's go back up here. A steady 100 kilometers per hour. How far did she have to travel to get home? 250 kilometers. So how long would it take her to move 100 kilometers per hour, and she has to move 250 kilometers? 2.5 hours. So one way we could calculate that is if we know, so on the way home, you have to make a graph still, so make sure you have room there for your graph. So write kind of smaller if you can. So on the way home, what distance does she have to travel? 250 kilometers. What speed is she traveling at? 100 kilometers per hour. And so if distance equals rate times time, we can sub in what we know. We know the distance she has to travel is 250. We know the rate is 100. We want to get t by itself. So 250 equals 100 times time. What do we do to both sides? Solve for t. Divide by 100, and that gives you the 2.5 hours. Some of this you could probably do in your head, right? Okay, so let's make our graph now. Hope you still have room. Now we're graphing distance from home versus time. How far does she get away from home? 250 kilometers. So we need to go all the way up to 250 kilometers. And how long is she gone? Well, now we know for sure it was 7 hours. There's that extra 2.5 hours to get home. Okay, let's make our graph. So we have to go all the way up to 250. What do you want to go up by? 20s? Remember, you have to input 140 in there too. Okay, 0. So we have our distance from home, which is different than distance. The units in kilometers. We're graphing it versus time in hours. We have to go up to how long in hours? 7. So we have 1, 2, 3, 4. This is where having graph paper is going to be very helpful, or a ruler, because you'll notice my half points aren't always the greatest. And we need to go up to 250. It's up to you how you want to do that. I am going to go up by 20s, I think. Maybe 50. Actually, I'll do 50s. This is how I'm going to do 50s. Watch this. Okay, 50, 100, 150, 200, 250. And then, if you really want to be, I don't know, accurate, you can go add your 4 dashes in. 1, 2, 3, 4. 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. But you don't have to. That's the best I could do without a graph paper. Looks okay. Okay, now we can graph. Now we're doing distance versus time. In the 1 hour, are we the whole time at 100 kilometers, or are we going from 0 to 100? From 0 to 100, right? We're moving a distance. In 1 hour, we get to 100 kilometers. At half an hour, I should be at 50 kilometers, right? Because this is distance versus time, not speed versus time. So now this is where it's going to always be a gradual. Our lines are not. Okay, then what does she do? 4 kilometers more. Is that more away from home or towards home? Another 40 kilometers away from home, so we're going to get to 140 at 30 minutes. And notice the slope is not as steep. She's going slower, so the slope is going to be less steep. Notice I'm using a word slope. So slope is going to be a very important word the next 3 units. And last, how far does she move the third interval? 110 kilometers, so that brings her up to 250. And how long does it take her to get there? 1 hour, so until 2.5. So that should technically be at 2.5. Right, 2.5 and 250. Now what does she do? She stays for 2 hours. So what happens from her distance from home? Stays the same. So it's horizontal. So from 2.5 hours to how many hours? 4.5. Because that's 2 hours time. It's a horizontal line. Because she's staying at the meeting. So she stopped. So it means her distance from home is still, yeah? Oh, so this was at 2.5, right? This one? This one? This one. Okay, so this is this one? I don't know, there's one right here. Okay, this guy is 1.5 and 140. Yeah, 140. This guy was at 1 and 100. And then we had 2.5 and 250. And now 4.5 and 250. Okay, now, what does she do now? She goes home. Is that going back to 0 or upwards? Back to 0. And how long is that going to take her? draw it to 7, which is a straight line to 7. It's going to take 2.5 hours, and then she's going to reach home after 7 hours. Reach home after 7 hours. So that's 7 and 0 now. Okay. Now, what's the difference between distance from home, like this graph we made, and time, and the next graph, our total distance versus time? It goes up the whole time, including at 0? No. Instead of going back, we're going to go upward to what amount? So if she returned 250 kilometers home, our total distance traveled would be 500 kilometers. So the next graph is not relative to home. It's just total distance. So we can do this one pretty quickly. We're going to do a rough sketch. Our time is still the 7 hours. I'm going to go down this. Has a not very straight line. Try that again. Okay. So 1, 2, 3. Ooh, that's bad. 4, 5, 6, 7. And so how much total kilometers does she put on her vehicle in this trip? 500 kilometers. So we have to go up to 500. So start by doing hundreds. 100, 2, 3, 4, 5, and then we can add in our 50s. 3, 4. We'll do a rough sketch. So add in our 50s. And so will this graph be very similar to the last one? No? So the only part that's different is which part? Instead of going back down, so the last line is the only one that's different. Everything else is the same. So for the first hour, she still travels how many kilometers in the first hour? 100. So she still goes up to 100 in 1 hour. And then in 30 minutes, she goes up to? How far does she travel in 30 minutes there in the construction time? 40 kilometers, so up to 140, so roughly. And then it takes her 1 hour to get to, she's traveling at 110 kilometers per hour, to get to 250. So 2.5 and 250 now. Right, so this point is our 2.5 and 250. Then what does she do after she gets there? Wait, 2 hours of meeting. So we get to 4.5. Just staying put. And then she goes all the way up to 507. So 7, 500. The only part that's different is this last part. So we're doing total distance traveled versus time. So it's like graphing her mileage on her vehicle over time. So this was 4.5 here and 250. No, but if you don't have like a graph paper, it's helpful. It can be helpful, right? For you, even? Okay, any questions about that? Okay, so turning over to the next page. We're not going to look at example 5, but just really quickly, if you're dealing with a speed time graph, okay? If it's a speed time graph, so if this is like your speed versus time, a straight line, a linear line, okay, a straight line shows uniform motion, a constant rate of change. So let's get back here. Constant rate of change on a speed time graph. So what does this straight line mean? Is my speed steadily increasing?
Yes.
Yeah. So it's a constant rate of change. Rate of change is not constant, and then no rate of change. And that's just in general, just a review. Okay, very similar to physics, something you'll see in Science 10. All right. The homework for today's lesson. No, we're not going to do example 5. We're going to omit it. So homework for tonight is page 281. We're not done for today because we have to keep continuing, right? So will there be a quiz on this tomorrow?
Yes.
Yes, quiz tomorrow, 1 tomorrow, 2 the next day. Okay?